Hello, my name is István and I'm currently working for Stream HPC. In our previous projects, we had problems and solutions for random number generation usage, and that's why we would like to discuss a little about random number generations on GPUs. Let's first mention the company. Currently, we are a GPU software development company working for companies in North America and Western Europe. We mostly do the development part of the research development, and our motto is that we make fast software. You can see a few partners and memberships in the top row. Currently, we have projects with AMD. We are part of the Kronos group. We had previous project with Stanford University Department of Chemistry, where we had to improve some kind of quantum chemistry calculations. You can also see our few customers. Currently, basically, we mostly implementing algorithm on GPUs, and we try to optimize it for customers. We are also doing consulting, and we try to teach the customers how to move forward with their project with the GPU solution. Our topic will be the random number generators. During this case, we would like to discuss, maybe touch the cable and pray. Okay, so we would like to discuss which random generator should we choose during our implementation. Why is it so difficult to use random numbers generators during a GPU implementation? What can be the pitfalls? And also, we would like to discuss few random number generators. We implemented the ROC-RAND library, an open source library for the AMD. Basically, that ROC-RAND library is the mirror of the current library. We worked on that. We should discuss few optimization steps there. And I would like to also talk about about the AMD's solutions, which you can detect and maybe you should use in the future. So, previously I worked with the guys from the Mediso, and there was always some kind of questions. Maybe we should change from the CUDA and we should use something different. And we had the same answers always. It would be expensive to change. If we change, it's also maybe a hardware change can be related to that. So that's why it's really interesting that the current ROCm platform can give us a very good solution where you can basically implement C++ code. And the ROCm platform, we used specific compiler to create the binary for NVIDIA cards or maybe AMD cards. You can use a portable source, not the binary, and with one source code you can try out different hardwares, which can be very useful. I also mentioned a few libraries which the ROCm can offer now. There's the ROCtrust and the HipCap. Someone maybe know those as Trust and CAMP. Basically, these are the ROCm solutions. So these are important because basically with these libraries you can use TensorFlow, just switching those libraries. The ROCtrust interface similar as the Trust interface, and you can use the TensorFlow with AMD cards and the Caffe 2.2 if you just replace the trust under the TensorFlow. We will talk more about RockRand in this presentation. When maybe you think to switch to EMD, please make sure that your CPU can support the EMD cards. Currently, there's some kind of request or requirements. The EMD cards can only work with PCI Gen 3 and PCIe Atomics support. So please check these before you want to change. So we had always the excuse as developers, it's time to implement something for different hardware. Now we have the Hippify tool. This is basically a script, and it will just create an equivalent C++ file from a Q file, and you can see the differences which this tool can create with a kernel code, and what can be the Hippified host code. The similarity are large. I think that's also something which can help the developers, because you don't have to learn too much new namings. There's always some kind of equivalent for the CUDA solutions, and like if you just check the block IDs, there's a hip block ID on the hip side, so it can make much easier. And I think only one manual step is here, that you have to always add the hip launch param to the kernel code, but basically it can be mostly automated to convert your current CUDA implementation. Yeah. So when you have the platform, and when you have the driver, when you have the hardware, and you made the decision which problem you want to solve, probably you will have to use random numbers. And we will discuss it, why is it not so simple, and we will discuss few random number generators. My first question, what do you think? Is this some kind of random color here? Yeah, so few heads, I can think it was yes. Basically, this is just the P number digits in the image. We attached colors to the digits, and we will discuss the P number. The P number can be also used some kind of random number generator. This is an unproved normal number, which can be almost good random generator. On the statistical test, it can also show a lot of passes. We will discuss those tests later. So let's talk about random numbers. What is a random number? Basically, separate random number do not exist. We can just talk about random number sequence. What are the requirements for this sequence? The values are uniformly distributed, and future values are not depends on the previous values. We have to follow these two rules to get a good random number generator. Where should we, or where they are using currently these random number generators? The obvious answer, lottery. Also now they are using cryptography. And also there are a lot of simulations where it can be useful, numerical analysis or Monte Carlo simulations. For simulations, it's not only for the random cases we want to simulate. We can use the random numbers at simulations for non-random cases. like we use the Monte Carlo methods to calculate some kind of integration. So let's talk about the different random numbers based on how we create these random numbers. There are hardware-based solutions. The problems with these can be slow. We can maybe introduce vulnerabilities into these random number generators, not reproducible, and non-deterministic. We will talk about this later. We can also use tables. Basically, this solution where we have a random number sequence and we copy it some kind of memory or table, and we use this. The quantity of this solution is limited, and also it can be fast, but we have requirements at storage part. And also the most common solutions, the algorithm-based generators, the pseudo-random generators, or some quasi-random generators. These are really fast, and these generators can reproduce the same sequence after each run, so it can be useful for tests. One problem with the pseudo-random generators, we do not follow most cases one rule. The future values can depend on previous values. We will discuss these. Which solution depends on previous values. So the hardware-based solution, in the past there were interesting ideas. The 8-bit Ataris used thermal noise diodes or resistors, and also now currently the Intel Ivy Bridge has integrated hardware-based solution. Most of the time these generators are using the hardware entropy sources. The problem with these, we have to process these entropy sources to get uniform random distribution, and that can be slow. And also we can introduce vulnerabilities. Sometimes it can depend on the environment of the machine, and it can also create problems. So that's why it can be useful to use some kind of algorithm to generate your random numbers. These algorithm basically wants to get random pair in a sequence, and to prove that, most of the time we are using some kind of statistical tests, and now there are a lot of test suites outside which can be used to test your random number generators. Most of these pseudo-random number generators has cycle length and a period. Not all of the random number generators have a tail, but we can get a period with this algorithmic solution. So we will have to check all the time that the period is enough for us, and we do not introduce problems with overlapping these random numbers during our calculation. Our aim with these generators to get uniformity and get long cycle. And another very important goal to get low computational cost during this generation. So let's talk about the normal numbers. If we just put history here, the past tried different normal numbers. We are talking about normal number when the number digits appear in a uniform distribution. And also we have proved normal numbers currently. Yeah, that's great. The spaces are perfect. So if you check the Copeland-Erdős constant, you can see the digits are just primes, and these are proved normal numbers. But these normal numbers currently mostly failing all of the statistical tests. The not proved normal numbers like P and E passing a lot of statistical tests, and it can be used as a random number generator. So let's talk about how we can generate these numbers. I think the first version was implemented by Neumann. They try to, and they have to replace a few cases the table-based solutions with other solution, and they created a simple equation where they are using the previous number to get the middle digits of this number and get the next number. It's also important which number you use for the start. If we get 0, it can create the end of our period. So that's why they started to realize the parameters can be important for these solutions. And the first version had limited period, and it was not stable. That's why they introduced the linear congruent generator, which is a very simple calculation. Here you can use so here you can use the previous number of your random number generator, multiply with a constant, add another constant, and use modulo operator to get the new number. If you choose the modulo m parameter correctly, which is your the limit of the data type, that means you can drop the modulo and just use the digit overflow to module your number. They realized these generators can't work every parameters, and that's why they introduced few rules for these. First rule was to M and C should be relative primes, and if Q is a prime number that divides M, then Q divides A minus 1, and if 4 divides M, then 4 divides A minus 1. They realized these rules are necessary to get a long period. Not every time you can get the period B as M number. The maximum period with these generators can be M, but to get that period number, you have to follow those 3 rules. And also there's a multiplicative linear congruent generator, which are currently using 0 as C. So here's a simple example for the parameters. ACM do not change, and x0 is the first number of your generator. How to calculate the next step? Basically, just put it into your equation, and you get the next number, and go on. And yeah, so these are fast, and with the tests are well proven and good generators. There's limitations when we try to sample with these numbers into hyperplanes. We can get periodic results, and that can be a problem. And also the period length can be also problematic. We can use large thread numbers, so we have to make sure that our period number is larger than our thread number on GPUs. That's why it's important to know your random number generator. Another solution is the lagged Fibonacci solution. It's lagged because we do not use the we do not use the previous and the before that number. We just use a number previously at the K status, and with this we can get bigger period. We can introduce a generator with the period here, you can see. And also there are more alternatives which try to improve the period length of these generators. There's the multiplicative recursive solution and the Mersenne twister. The Mersenne twister using 624 numbers to store that state. And with that solution, you can get a really large and very long period. That means probably during the runtime, you will not overlap and use the same random sequence during the calculation. I'm also trying to mention this as a problem because at Mediso we had problems with it. We had to switch our random number generators because we got during the simulations bad results. That's why is it important to choose your random number generators for your problem. These are two other random number generator here. So, yeah. After time, they introduced much better solutions. Marsagli is a very strong name in this area, and he created a lot of simple but very good solutions with large period and very good statistical results. I think the Sorval is a very good generator, and you can get a really long period with this. And it's also very fast and do not use too large resource on the GPU. And it's just few calculation steps to get the new number. What the solution when we do not want to get uniform distribution? You can create, if you can create the inverse distribution function, you can sample that function and you can get a custom distribution. Sometimes it's not a solution. In that case, you have to use some kind of rejection method, and you can create a custom distribution, and you can sample your random numbers on that custom distribution. What can be the problem if you want to run these RNGs in a parallel way? You have to find the perfect seeds, and you have to avoid the overlaps. I already mentioned that. You have to prepare, and you have to find a generator with a long period, and you can also solve that problem with different parameterization of your generator, but for that you have to, okay, sorry, I will wrap up everything. Okay, so basically the important part is that you can use methods to get seeds for your random number generators for the different threads, and also you can use different parameterization for different threads. If you move forward with the different parameterization, you will probably get limitations, and it's not easy to get different parameters for every thread, and you have to test all those parameters. Are the random number generator statistically correct? If you want to test your random number generator, you can use statistical tests. There are a lot of suits, and you can also find the diehard. It's a very common package where you can create test cases where you can detect your random number generator distribution. We have no time to discuss this currently, and let's jump on the libraries which are important. As I already mentioned, if you do not want to focus on these topics and you want to avoid this, you can find very good solution. But you have to know what you are doing, and you have to understand the background of these solutions. So the currently offer really good solutions, and you can find different generators there. If you just want to use a simple solution, now you know that you have to create some kind of state of your generator. That's why you have to call probably a host site initialization for your state, and then you can call at the device size the random generator, which are just using that pointer, and you can get a new random number. It will take care of your thread IDs, and it will use your thread IDs and will get the state for your current thread, and it will take care of your seeds, and that can be handy. Our team worked on the Rockrand, and before optimization, we had a comparison with the Courant and Rockrand. As I already mentioned, we can run the Rockrand on NVIDIA cards too. That's why the 3-column Rockrand with Nano, Rockrand with GTX 1080, and Courant with GTX 1080. You can see the throughput in gigabyte per sec. These are the generated numbers in bytes, gigabytes per seconds. After the optimization, which was a basic introduction and using an instruction in the Rockrand. Funny thing that after we added this into the Rockrand, the Courant also integrated this solution into their library, and currently the difference are not so big between the Courant and the Rockrand implementation, but at that time we get really good results with a few generators where we use that assembly instruction, and it can be also useful to try to introduce those instructions into your code if you want to get better performance in the future. So you can get more information here. And sorry for the problems in the beginning, and sorry that I had to be fast at the end. And if you have any question, I'm here.
Questions? So one problem I often have when I work with randomness on GPUs is that I have one random number state, and then I want to launch 1 million threads that each generate their own random number stream. So do we have any solution for how to split one state into an arbitrary number in an efficient manner?
I did not hear the question.
So if I have one random number state,
Yeah.
and I want 1 million threads to generate their own streams, so how do I split one state into an arbitrary number in an efficient manner?
Still hard to hear it, but I think the question is that the resource size can be really big for the current status. Is that a question?
Not just that, but how do I ensure that the states I get are good, that I actually get random numbers, that they're not correlated between the threads? That's my main worry.
To do that, if you are using some kind of linear convolutional generator, you can use the leapfrog method, where you jump a larger period that you have to prepare for the large period. That's one thing you have to take care of. I think the libraries which are offered by the Current and the Rockrand are very good, and they try to hide these problems from you. So just basically you just request the large thread numbers, and you have to check the period length of that your generators, and if the length are good enough, then probably you can use that random generators from the library.
Okay, further questions? Oh,
I had one question regarding Rockrand. I peeked at the sample codes on the GitHub site, and there was in C++ 11 the random number generator library was introduced, which is very good in the sense that you can generate arbitrary distributions because the choice of distribution is separated from the random engine. And as far as I could tell, Rockrand did not make this distinction, like to separate the random engine from the distribution. Did I see correctly or not?
I can't answer that question. I do not know, sorry.
Okay, thank you.
Okay. Any further comments? Okay, if there's no, let's thank our speaker again.